Well, good afternoon, everyone. I can see there's a few more people flooding into the webinar, but welcome to day 2 of our Unlocking Innovation Routes to Zero Carbon Rail webinar series. We've got a really stellar lineup of speakers today, so I think we should be treated to some really excellent presentations and some very thought-provoking discussion. What I'd like to say is that obviously this is part of a series of 4 webinars, and yesterday we covered electrification and how to do that more efficiently and faster, and that was really good as well. And that session was started by Network Rail, Helen McAllister from Network Rail, talking about the traction decarbonisation network strategy. And in essence, that strategy puts forward the proposition that we need 11,000 single track kilometers of electrification, and we need around 4,000 kilometers of something else. And today we are going to be focusing on that something else. So we're going to be very much focused on self-powered rolling stock, so non-electrified traction, and what the near-term and medium-term and perhaps even the long-term solutions for that might look like. So that is going to be our focus point today. The way the agenda is divided up is we've got 4, I would say, kind of meatier presentations to start with, and then we'll have 4 shorter 5-minute elevator style pitches. And then after that, we're going to have a question and answer session. Now, please don't wait until the end to ask your questions. You have the facility in the GoToWebinar platform to ask questions at any point throughout today, and I would urge you to ask your questions early and not wait to the end. Invariably, we won't be able to get to everybody's question, but the presenters are able to respond to your question using the text facility in the platform. So when they finish their presentation, they'll start going through as many of those as they can get through, and of course we'll have the verbal Q&A towards the end to ask any that don't potentially get answered by the presenters. In addition, the handouts, so all the presentations, the handouts for those are also available in the GoToWebinar platform sidebar or panel or doc or whatever you want to call it. So if you look in there, you should be able to download the handouts for each of the presenters. So I'd urge you to do that. Of course, we are recording this, and that will be made available tomorrow on the RIA website. So you should be able to download the recording for the whole webinar and all the material as well. So without further ado, I'd like to introduce our first speaker, who is Brian Reynolds from Angel Trains. He's going to kick things off from a rolling stock owner's perspective, and I guess showcase some of the work that you've been doing, Brian, on hybridisation. So, Brian, over to you.
Thank you very much, Trevor. So thanks for the introduction. As product manager for Angel Trains, I'm responsible for the long-term development of Angel Trains' existing fleets. And I'm going to talk to you today about ways that we can contribute as a Roscoe to the wider decarbonisation agenda through upgrade and modifications of our existing assets. Hopefully, we'll show the thinking about how we can reduce emissions from our existing trains and contribute to the decarbonisation effort in the short term for the whole railway. And in the meantime, or medium to longer term, allow necessary infrastructure to be built for the longer term solution. So I'm going to first talk a little bit about the decarbonisation challenge, and then give you the update on Class 165 self-charging hybrid. So thinking about the drivers for decarbonisation. First of all, in early 2018, there was the then Rail Minister Joe Johnson, who issued a challenge to us all: remove diesel-only trains from the railway network by 2040. There was a task force set up, as hopefully most of you know, and the no diesel-only by 2040 target was deemed achievable for passenger rolling stock, but not potentially for freight. There was a whole different set of challenges set aside for freight decarbonisation. The task force also noted that Britain was aiming for a net zero carbon emissions by 2050, a target that goes beyond the requirements of the 2008 Climate Change Act, but it was deemed technically achievable, certainly for passenger rolling stock. But more significantly than maybe legislation was the weight of environmental and public opinion. Certainly in a world where generally we're becoming more aware of our impact on our environment, a world where diesel bans and emission charging are becoming increasingly commonplace in road vehicles, awareness of emissions from diesel trains is also obviously increasing. Now, we've got to remember that we in the rail industry are only responsible for around about 2% of the CO2 output of Britain's land transport. Our output is set to reduce further, obviously, as the grid electrical supply is further decarbonised. But you've got to remember that when you're stood on Birmingham New Street Station with a DMU on either side of you, churning out some quite nasty emissions, we can't afford to rest on our laurels. We've seen massive development in electric cars, and hybrid and hydrogen buses are actually physically out there on the streets. So the rail industry needs to work hard to retain our environmental advantage against those other modes of transport. So I wanted to show the CO2 emissions from rail traction that has been put in the RSSB research project. And this chart is quite revealing, really. Firstly, the thing that we spot is that hydrogen does give zero emissions at the point of use, but it's important to realise that the source of hydrogen plays a massive part in the overall well-to-wheel emissions. So if you look there on the chart, some of those methods maybe actually aren't any better or potentially worse than diesel overall from well to wheel. Secondly, if we were to hybridise our existing fleets, there is a potential to save between 1/4 and 1/3 of the emissions that we're currently producing with just diesel trains. And that's without the need for any additional infrastructure. And thirdly, gas engines provide a step change in CO2 emissions if we could retrofit the diesel engines, but that's a topic for another time. So, moving on and thinking about those traction options that are available. Electrification. I think everyone understands that electrification is the best way to give a decarbonised railway, but there are obviously barriers in the way, the infrastructure not being available, for example. We recognise that the whole industry has a collective fingers burnt with time and cost of overruns of previous electrification programmes, but it shouldn't detract us from the fact that electrification, if of highly used, higher speed routes, is the most effective way of decarbonising the railway. So if we want to recognise that electrification is not an overnight solution, especially if we want to grow and retain the skills through managing the rolling stock programme, rather than the boom and bust approach that has often been employed in the past. So, thinking elsewhere from electrification, there's the battery option. Battery trains have generally constrained to shortish self-contained lines, as currently demonstrated by the Viva Rail battery-only version of their Class 230. Battery power density and the charging technology is going to improve in the future, I'm sure, but it's extremely unlikely that this range will increase in the medium term. However, batteries on their own are unlikely to provide viable solutions over the longer distances. So what can we put in the middle? Well, obviously there's the gaseous versions. So the hydrogen, for example, the range is at the moment around about 600 miles by the seam of it between refueling events, as opposed to diesel trains of around about 1,600 miles for conventional DMUs. More frequent refueling stops and refueling during the day, more refueling points of infrastructure and additional staff, and probably also more trains. So that's necessary infrastructure to generate, store and distribute hydrogen as a fuel source for mass transit doesn't quite exist in Britain, if you might have noticed. But if it's supported by government policies on energy, industrial strategy and transport, renewable energy can be used to produce green hydrogen during periods of low grid demand, which is then stored locally and used to either power transport or to convert back to electricity when the demand is higher. And that is an example that we've seen so well presented with Alstom's iLint in Germany. And Transport Scotland has recently articulated its vision to use renewable energy to produce hydrogen to power trains, potentially on the West Highland line and the North lines from Inverness to Wick, Thurso and the Cardiff Lockhouse. So what else is there? Another option. Well, the bi-mode trains. We've all experienced these. Diesel electric bi-modes gives the advantage of electrification where it exists, and switching to the independent power source where that's required and the electrification doesn't exist. It can eradicate the problem of running diesel trains under the wires and give the time to electrify the rest of the route. But bi-modes are not optimal, and you have to carry around 2 traction systems, meaning that you're always carrying around a dead weight, whichever traction system you're using. Then there's the battery electric mode. You could power the train through gaps in electrification infrastructure, potentially lowering costs by avoiding the need to electrify complex areas. This has been shown to be feasible back in 2015 with the IPEMU trial, with a last mile solution option for things, routes like Oxenholme to Windermere, potentially. And then finally, we've got a hybrid option, and that's what I'm here to speak to you today. We can go beyond battery range alone, and we can cover non-electrified routes currently operated by diesel trains. So a diesel-powered train with a mechanical transmission, with a battery as a means of recovering braking energy and a potential boost when required. Or you have a battery-driven electric train with a diesel engine as an onboard generator, effectively a range extender that keeps the batteries charged up. So each of these provide a significant reduction in overall emissions, coupled with the ability to switch off the engines in the stations and sensitive areas. And this latter option, which is a series hybrid, is the arrangement that Angel Trains and Magtech are advocating, and that's what we're going to talk about now. So the further benefits of the decarbonisation side for hybrids is that there are 11,700 single track kilometres of railway still to electrify, and the Traction Decarbonisation Network strategy identified that potentially 400 of those single track kilometres could be battery operated, 900 hydrogen, and 2,300 single track kilometres where there was no clear technical advice, and that's where our hybrid comes in. So the Class 165 hybrid drive, there's the potential future livery, just to get you all excited. So let's talk about what we're going to do. So the electrification program is going to take time, as we've summarized. Hydrogen will be a longer term solution, but what do we need is that stopgap, hybridization. It's immediately available, no additional infrastructure. We're still using diesel at the moment for the range generators, so that's a very quick win. Overall, the local environmental improvement with engines switching off availability, very low embodied energy because we're using trains that exist already and have life still left in them. If we were to replace those with new trains, then that's quite a lot of embodied energy that we will have wasted. And there's benefits to operators and passengers, as I'll mention in a moment. And it gives us a short to medium term upgrade path to allow time for the infrastructure to be brought up to speed with either hydrogen generation and distribution points or electrification. So the current Class 165, as you'll see here, has hydrostatics that drive the transmission, powered by the engine, and there are a small set of batteries for starting and onboard ancillaries. So we're going to remove all of those, or we have removed all of those, and we're going to fit new equipment. We've got controls and RCM that give us the latest technology of reliability-centered maintenance and remote condition monitoring. We've got a 400 kilowatt traction motor, which we'll be limiting in our 165 application to 300 kilowatts, producing 4,000 Newton meters of torque. Enough power and torque to start the vehicle with one of the vehicles out of service for whatever reason on the steepest incline in the network, so giving redundancy. We've got a new IGBT power system, intelligently controlling the power flows in both directions, which I'll mention in a moment. And two 120 kilowatt engines used as generators, those range extenders that I was mentioning earlier. The system is modular in design, meaning that the range extender engines can easily be replaced in the future, either with more batteries or potentially to create a pure battery train, or use different range extender fuel, so for example gas engines, or indeed hydrogen in the future when the infrastructure is in place. So the electric driveline opening up many more possibilities for the future. So let's do a quick hybrid run through. So engine and battery mode, that's in general the normal operating mode. It provides the train with its primary power source and the range extender engine, keeping the generator and batteries topped up. The power flow between the range extender engines, battery and the traction motor is intelligently managed to deliver demanded power of the traction motor whilst keeping the battery within its optimum discharge cycle. The system can also operate in battery-only mode, and this will be around stations, depots, and other environmentally sensitive areas. We use GPS location for geofencing, and the range extender engines are switched off and made sure they stay switched off in those areas, so we are truly zero emissions. In practical terms, for the pilot that we're doing on Chiltern Railways, that will be geofenced in stations, and the approach to London, where we'll switch off the engines as we cross the North Circular Road, meaning that the last few miles into Marylebone and back out again, inside the Mayor of London's ultra low emission zones, will be emission free. And then finally, the best benefit of the hybrid, the regenerating mode. When we're braking, we won't be using brake pads and creating dust from those brake pads. We'll be regenerating the power for slowing the vehicle down and recharging those batteries. So in summary, the hybridisation of existing fleets can bring about a number of benefits in mutual areas. Environmental benefits, overall reductions in CO2 emissions of around about 25%, and significant reductions in NOx and particulate matter, coupled with not losing the benefit of the embodied carbon in the train that's physically in existence already. Passengers experience better air quality in stations. The engines will normally be off in those areas, and a quieter passenger environment on board, as engines will be at constant revs rather than throttling up and down, because it's the best point to operate those engines. There'll be operational benefits, including reduced fuel and maintenance costs, and increased range, giving flexibility and a reduced number of depot visits required. And there are also performance benefits. These are possible through the improved acceleration capability offered by a more efficient driveline, giving the potential for improved journey times and more frequent services. And overall reliability will be improved through the removal of some of the most problematic components and systems on the train, and their replacement with equipment which is inherently more reliable. And finally, the green upgrade path that I mentioned at the start, affording by essentially moving to a battery-driven electric driveline, meaning that the range extender or battery chargers can be replaced without further major surgery to the train. So that's the decarbonisation challenge that will mean radical changes to the way that we power our trains that are not currently electrified in the medium to long term. It means retrofit options such as hybridisation could provide a stepping stone towards a zero carbon future, providing immediate environmental benefits with no infrastructure requirements, modular approach to future upgrade potential, and having engines off in stations improving air quality and reducing noise. So that's it from me, hopefully just about 15 minutes. And I hope I've given you an overview of the potential benefits in terms of the environmental performance, reliability, and operational flexibility that can be achieved by hybridisation through existing diesel fleets.
Many thanks, Brian. Very interesting presentation. You've stimulated a load of questions, so I'm be grateful if you can divert your attention to those as we move on. So next up, I'd like to introduce Jonathan Brown from Ricardo. And Jonathan is going to come and share with us innovation in decarbonisation and how to make it work. I mean, that's a very big question, Jonathan. I hope you can pack that down into 10 minutes. So good luck.
Probably not, but we'll give it a go. Thank you, everybody, and welcome this afternoon. And yeah, thank you, Brian. Really, really interesting. So I'm going to come at it from a slightly different position, which is not any particular product or technology, but talking about how can we make innovation work, because particularly in decarbonisation, it is a challenge in rail. We see a lot coming out there. How much makes it all the way through and into real world service is slightly more questionable. Just very quickly, who are Ricardo? Some of you may have heard of us, some of you may have worked with us, some of you may never have heard of us at all. We are a business that's sat in the background behind other businesses for over 100 years now, principally designing propulsion systems for everybody and anybody. Any big name badge will likely have some Ricardo technology behind it somewhere. But we also have a rail consulting business, and we also have an environmental and energy consulting business as well. So all of these work very well together in terms of how do we decarbonize in rail. So I think we'll take a quick step back before we get too far on in what is innovation. Innovation is a term bandied about a lot. I think lots of people think they have a good idea what it is. I find the reality is it seems to be a bit more woolly, and it's very difficult to get a really clear view on it. So a couple of years ago when I was getting into innovation, I went and did a bit of searching about what it is, found a lot of innovation specialists, and on one site, this chap Nick Skiddicorn, he came up and he had done the same thing that I was trying to do, so I thought I'd use his work very kindly, which said, what is innovation? So his view was turning an idea into a solution that adds value from a customer's perspective, and I like that. It is about the adding value, and that's something that is often lost in translation. However, just scouting around a bit more, there are various other views on what innovation is from people who work in this business and in this world, and none of them are particularly consistent. And in fact, actually, if you look at the dictionary versions of innovation, even the dictionaries do not have a consistent view of what innovation is. Here we have something new or different. There's a new idea, and introduction of new things, ideas, or ways of doing something. So the word new is often in there, but then I would hark to say it's not always new, and I think that's the view from a lot of people. And we come back to Nick and his view that he took all the ideas of innovation and said, what are they? And actually, so he comes up with executing an idea which addresses a specific challenge and achieves value for both the company and the customer. Now, the company doesn't have to be a private enterprise. The company is effectively the one proposing it, and the customer is the one that's going to use that innovation. And I think that's really important to think about, and how we frame the question of how we make things work, because it's focusing on the challenge and the value that we're going to derive from this. So a quick story of innovation, as we like, just to sort of set it a little bit more. We've seen recently lots of talk about battery electric trains. Over in Germany, OBB have got some battery electric trains from Siemens going into service. We mentioned Viva Rail earlier in the previous presentation doing battery trains, and I am well aware that many other OEMs are working on battery electric trains. These are something new, right? Well, not necessarily. Here we have in front of us the world's first zero emission, zero carbon electric train, battery electric train. This particular train is zero carbon because it was actually from North Scotland, from the Northern Scotland Hydroelectricity Board. They sponsored this train where, at a time in the early 1950s, the line was financially unviable to run with a diesel train. So they said, look, we've got lots of excess electricity up here from our hydro dams. Why don't we convert our train that's got diesel engines in, stick some batteries in there, and then we can run the train on the batteries? And they did this successfully for a number of years until they upgraded the battery systems, and unfortunately they were not appropriate batteries. They caught fire, and the train was parked at that point. But that was genuinely a zero carbon emission battery electric train in 1954 in Scotland, running in passenger service. It's not new. The problem is, at that time, the value of it, i.e. zero carbon, was not considered, not understood, and not appreciated. So it was a great idea, but at the wrong time, possibly in the right place. And that's part of the thing of innovation, is understanding what the value is and looking at all the different parameters that can combine to that value, and making sure that the users and the customers and the stakeholders understand that. So I think it's sort of a salutary lesson. So where are we today? Well, a little bit later on, we're going to hear from Mike and the great success that Alstom have had with the Alstom Island train in Germany. Run a year and a half of operations over there, and they're now moving to passenger service in Austria as well. So this is from September this year. So great news that the island is spreading and growing, and I think that's excellent for us. Within the UK, a good news story here recently. Porterbrook have got their Hydroflex, a hydrogen train, onto mainline testing. So that's the first hydrogen train mainline testing in the UK. So you could consider all of these sort of successful innovation. And I would say yes, to a point, but certainly within the UK, we are yet to see the actual or the realization of these in full service. Whereas in other industries within the transportation sector, really we're quite a number of steps ahead now in hydrogen use. So how can we accelerate that a little bit more in rail? And I think the first thing is we have to ask why. Why is it so hard to accelerate things in rail? Well, firstly, the environment, the industrial environment, is a heavy industry. Things have to last a long time and perform well over those times. So it's really a big challenge. Secondly, we've got stakeholder investment. It's a really fractured industry with multiple stakeholders and multiple people who have control of purse strings, often with different drivers behind them. Clear policy and consistent regulation. I think many could claim there has not been clear policy for rail for some time, or consistency of the regulation. It chops and changes. We have the SRA, then not. We've got ORR, RSSB in various forms over the years, and we are never quite clear from the guidance from above where we are and how we're going to manage. Next, we have industry drivers. So the rail industry is not set up as an industry ready for decarbonisation. The rail industry is still fixated on timetable and scheduling and delays, and everything runs around delays. There is no value assigned at this time to carbon, and that's really a killer when it comes to innovating with carbon. Part of doing that would be taxation and charging and incentive schemes, but again, there aren't those. There are those in road transport, and hence we've had reductions in emissions. We've had harmful pollutants, and we've also had reductions in carbon. And then finally, we've also got standards creep. So this is an industry that's had 200 years of standards development, and standards build on standards, and rarely do we go back with new tools and new technologies and really validate, are those still necessary? Hence weight and cost go up, and the effort to apply new technology is exorbitant. But trying to be quite quick, we won't dwell too much on this, but there are some examples of challenges in rail freight that we were looking at recently in terms of decarbonisation there, and we're looking at issues in the short term about space, about how you apply all these things within the existing vehicles, and also about how government is not supporting that with clear policy. And then within the longer term, it's really about proving the technology. So what are the additional requirements? How do we prove that the technologies are ready? What are the different range of solutions, and how is the infrastructure ready? And that's really important. Is the infrastructure moving at the same speed as the technology on the vehicles? We're just going to finish up with, well, how do we do it in other industries? This is an example here of designing a hydrogen fuel cell truck. Well, hybrid, I guess it has a battery system in there as well, but effectively a hydrogen propulsion Class 8 heavy haul truck in the US. This was a project Ricardo been running with Toyota since 2015 now, and we designed them a first generation truck that ran around in the port of Los Angeles doing drayage operations for about 2 years, very successfully. A second variant has come out of that, improving the range and the performance of the truck, and the third variant is now out on the road, which is looking at much more going into a production style environment. And we're looking at now volume production for the first off-the-shelf volume hydrogen fuel cell truck, which will be available by all accounts within the next year. You can already take orders for it. So how do they do that? Well, the successful projects really need the very clear business case. Don't forget to include your social costs with that. They need consistency of policy and market. They need a really clear understanding of the value to all the parties, so not just the financial one, and what the specific challenges you're addressing are. This one is really important. They need rigorous, well-executed engineering development programs. It's challenging in an industry where innovation is not the norm, such as rail, and it really has to provide both value immediately, and an immediately reliable and effective service when it goes into production. So that's really critical. So we have to engineer it right and understand the cost, but equally the value of engineering it right from day one. And finally, there's an appetite to challenge the status quo with our committed stakeholders And last but not least, we need collaboration and partnerships, even between competitors for that. So that's a very flying view of how to do innovation. And with that, I'll leave it there. Thank you.
Thank you very much, Jonathan. I'm glad you ended on collaboration. I can actually see in the questions there's already some collaboration happening, which is one of the things that we want to get out of these events. So, you know, part and parcel of unlocking innovation is trying to get, you know, suppliers to talk to customers and actually start to form those supply chains that are going to unlock some of this innovation going forward. So, yeah, excellent presentation. Thank you very much. I'm going to focus now down on one of the areas which you touched on in your presentation, which is freight, recognizing that rail freight is a particularly pithy problem when it comes to decarbonisation. And I'd like to invite Mike Edwards to come and talk. Mike is the CEO of Motive Zero, and he's going to basically present the work they've been doing on decarbonising self-powered rolling stock, but I think particularly with an emphasis on one of their freight projects. So Mike, over to you, please.
Hi, I'm Mike Edwards from Motive Zero. I'm very disappointed that I was the only one to actually bring a train with me. Everyone else seems to be working from home, so I'm definitely missing a trick. So we're all about unlocking innovation, particularly in the freight sector, has been mentioned. And I think has been alluded to previously, there's a lot of confusion as to what people are trying to achieve. So we know we've got to aim for 2050. Do we want to do that now? Do we want to do it next week? Does anyone care about emissions? Are they purely focused on costs? So we need to be clear on what problems we're trying to solve, and also whether we're trying to solve them with today's technology or tomorrow's technology. And what I mean by that is, do you want to make big capital expenditure in 2020's technology, when in 20 years' time, there will be something that's massively better? Or do you want to take what you've got and leverage those assets, have a rapid return on investment, so you're cutting fuel costs, you're cutting maintenance, and you're not spending millions of pounds on new locomotives, you're actually using what you've got. And as has been suggested before, having an upgrade path for these new technologies as they evolve. We're already getting some success of this. We've got a lot of people waiting to trial our locomotive. Started off with an 08 and have sort of moved on from there. But this is kind of our summary: enabling global train operators to meet the challenge of low carbon railways by upgrading old technology diesel locomotives with clean economic hybrid electric power. That's such a mouthful. What does it mean? Well, we're not just solving the emissions problem in the short and medium term, we're making it cost effective as well. So you can save your big capital expenditures for next decade or the decade after, because we can give you massive savings now. And this is all working incredibly well, starting with sort of small freight locomotives, shunters like the 08 that's behind me, or the 37s and going onwards. So effectively, we're producing a complete drop-in system. As you can see from the locomotive behind me, you take the engine out, you take the generators out, you take all the old wiring out, and what you'll get is in a crate, a completely new powertrain, drop it in through the roof, wire it up, and you're good to go. So we have significant fuel savings, significant emission savings. We can put regenerative braking onto pretty much any locomotive. Ones that haven't been there before, larger locomotives where you're currently doing big resistor packs for rear static braking, so it burns off the energy as heat. What a waste of energy. Why can't you keep that and use it? And we've got sort of fault reduction, increased safety. We've got sort of patents we're going in on wheel speed sensing. We've got advanced anti-spin, anti-skid type technology. So there's a massive benefit, which comes to the question as to, I seem to have lost the slide. A massive question as to why you'd want to upgrade. Well, we can solve a couple of problems here. We've got a selection of older locomotives. Your question at the moment is, how can we, oh, 08s are old and disgusting. We want something new. Can you buy new small shunter that's clean, is allowed to go out on the main line, etc., etc. Well, no. We can build you a new 08 that will have all that. It will have all the grandfather rights, etc. And it'll be able to be upgraded with clean air, etc. So we'll have a few of our own test vehicles, 08s and 37s, etc. But ultimately, we're here in sort of position 2 about producing and selling conversion kits. So that is, we build the kit, we give you the instructions, or give a suitable mechanical partner instructions how to install it. And with a very short turnaround, you can actually have your own hybrid locomotive. It'll just be the same locomotive with loads of new features. Here we go, here's the loft side. Why would you buy it? Grandfather rights. If you want to buy a Toshiba shunter or a brand new mainline freight locomotive, it's all got to be certified. All we're doing is upgrading the locomotives we've got, keeping all the rights that they had previously, and just getting new certification on the bits we changed. So we get all the flexibility. You can be electric only. Hell, the whole locomotive can be battery only if you want. We think having a range extender hybrid solution is the optimum for the moment. Our new speed power controls and traction controls allow us to give much faster response to the driver. You can get away from the signals faster, which has traditionally been a problem for freight. And this regenerative braking, it all sounds good, doesn't it? But it's only when you consider that it's the equivalent of up to 12 Tesla superchargers operating at once, you see how much energy you're missing out on currently. So there were lots of options. A simple Class 8 conversion for mainline access, even some of the proposed things like Class 93s. Why would you spend £4 million to make something better than a 66 when you could take a 66 and make it even better for significantly less money? So this is where we started. This is actually the loco behind me, pushing the Royal Train. So we kept the traction motors, the old compressors and things, removed pretty much everything else bar the driver's controls. And we've installed a new small hybrid engine charging batteries, a lot of new batteries, but also a new control system. And I think a lot of the, talking about the innovation previously, a lot of the innovation goes into the control systems as much as it does into the power systems. So here we go, here's a nice picture. You can have a battery only train, apologies to Duracell. You can have a diesel engine to charge the batteries. And one of the other products that the company does is some bolt-on technology that allows us to take a stage 3A diesel engine and make it cleaner than stage 5. And that's without any of the post-combustion rubbish that has to clean up your output. We just don't generate it in the first place. One of the advantages of not generating it in the first place is that you're more fuel efficient. And as you go, if you get new battery technology or you decide to dump that diesel engine, you can put in new batteries, hydrogen powered fuel cells to charge the batteries, etc. So it's a full range and you're not wasting your investment going forward. So what are we actually doing? Well, we started on the 08 and we've built a couple of those. We've got a lot of interest from lots of different companies for that. We're about to start on our 37 conversion. And the same technology scales up all the way through to 66s. So it's pretty clever how we can use the generator, how we can use the batteries, how we can split them out and use them in different ways if there are problems to get you home. So we work with lots of different traction motors. We can swap from a menu effectively of auxiliary systems, bigger or smaller battery packs, lots of range extender capabilities, and we can also do the AC systems as well. I just lost slide control. Can we just drop across the next slide, please?
Oh, I think we need to go back a little bit. Yeah.
That's it. Can you just go back to that last slide for a second, please? Hello?
Yeah, it's happening. There you go, Mike. It should come up in a second, hopefully.
That's gone back. That's gone back to the beginning.
I think it's the penultimate one he wants, Hannah, with the three locomotives on it.
Yes, that's it.
Yeah.
So here we go. This is our current focus. We've got quite a range. Oh, it's moved again. Can we go back a couple of slides? Back to the one with 3 locomotives, sorry.
That's the one we're on now, Mike, I think.
Yeah, the one before that. There we go. So you can see that there's an awful lot of different power outputs, a lot of different configurations. Mainline, freight only. I don't know why we've gone back another slide. But effectively, the key technology is regenerative braking, new anti-spin and anti-skid controls, more precise power delivery. We're also looking at some semi-autonomous usage, which will come along, all part of the same kit. And you can even have clean and filtered air if you want to. So there's a lot of technology there. I hope we've done it justice in the short time available. Thank you.
Thank you, Mike, and apologies for the technical difficulties there. It is extremely difficult for those of you in the audience who are not doing this, because there's a significant delay between pressing the slide button and something actually changing. So it's you have to be a bit preemptive. So Mike, thank you for bearing with us. I'd like to move on now to Mike Muldoon from Alstom. And Mike is going to come and talk to us about the Breeze project, which should be an interesting look at their hydrogen train. Mike, over to you.
Great, great. Thanks, Trevor. Yeah, I think amazingly, quite a lot of what I intend to say possibly has been points have been made by many of the other contributors already. So hopefully you'll find things that link up quite well in all of this. But as I think most people are aware, Alstom is the sort of world leader. We actually saw earlier our first train, and it's now my turn to have an absence of, there we go. Hopefully that isn't going to jump onto another slide in a moment. But basically, we have built the world's first hydrogen train, and for many of the reasons that have already been discussed. So recognizing that there is an imperative to replace diesel, not just for carbon reasons, although that's the obvious headline grabber. Carbon, of course, is the problem that's going to kill us tomorrow. Particulates is the problem that's going to kill us today, both of which are released by the combustion of diesel. So we needed to do something about it. But also because across the piece, self-powered trains, we need some alternative technologies. We actually started thinking about this quite some time ago. It was back in 2012 that we first started work on developing hydrogen technology for trains. And we unveiled the actual physical trains in 2016 at InnoTrans in Berlin, and they entered service in 2018. And as was mentioned earlier, we've already had over 180,000 kilometers of service in Germany, several thousand of tests running around the country, and also now in passenger service in Austria. So a proven product by any definition. And that technology was specifically developed to try and address some of the issues that we've already talked about so far today. But why have we even contemplated hydrogen as a thing? And I think whilst we can debate about what's today's technology and tomorrow's technology and the technology of the day after, at the moment, we can only work with what we have. And whilst we have a considerable amount of time, apparently, between now and 2040 or 2050, we're within the life of a train. So a train would be designed and built for 35 years, and we need to come up with solutions that can deliver. If someone wants to buy and operate a new train, ideally they don't want to be changing it in the meantime. But also we need to look at how can we actually carry energy on board those trains, and how are we going to solve this problem per se. And if we look at at the moment, the physical constraints around energy storage, diesel is absolutely brilliant, and that's the reason why we love it, and that's the reason why we've used it so much. Hydrogen offers the next best level of energy density, though as someone mentioned earlier, it's considerably less than for diesel, and in fact you need 8 times the volumetric space to store your hydrogen, even when it's compressed to 350 bar. So you've got the first issue there is how to contain your energy. If you wanted to double your space again, 16 times more space than the diesel and probably 50 times more in terms of weight, you could get the equivalent energy stored in a battery. And there you see the decision-making process that leads you to hydrogen. At the moment, there is nothing better. And the beauty of using the hydrogen is that you get elimination of all forms of emissions, not just the carbon, which is a problem, of course, if you continue to combust gases, even biogases, you get particulate emissions. And so by going to the use of hydrogen in a chemical process in a fuel cell, you can eliminate all of that emission problem. And we need to, because the networks are nowhere near electrified yet. The numbers were presented earlier about what TDNS, the Traction Decarbonisation Network Strategy from Network Rail, proposes. And what it actually proposes is the a huge degree of electrification in the country. And that's a great plan if we can deliver it. And their proposed program, I think, stretches over about 40 years. So we have a considerable period in the meantime, indeed the life of a train, in which we could be operating alternative technologies and making cumulative carbon and particulate savings between now and then. And I think that's all factors in deciding what it is in terms of the technology you want to use. Our imperatives, though, were set by Joe Johnson's speech. There's a little bit of it there. It's been referred to by at least 2 people, I think, so far. So old news, I'm afraid. But until that day, there was no reason in Britain not to continue using diesel. There was no contemplation on the rail system of the necessity for cleaner traction technology. It's only come about really since then, since it's been put on the map. And of course, Scotland has galloped ahead to ensure that it delivers first, and committed to something far more strenuous, actually, by 2035. And we have targets in Wales for net zero. We have targets in cities for low emissions, which Brian mentioned earlier. All of these things conflating to make it a real rush now to make sure that we can do something. And all of a sudden, that complacency about time starts to make you wonder about, should we not be doing something now? So we've set about to try and do something now, very much in the belief that practical steps can be taken, picking up, I think, on the point that Jonathan made around what is innovation and how do we deliver it, and actually achieving steps. Innovation isn't a pursuit in itself. You can't just innovate for the sake of it. But many schemes tend to do that. The much maligned and underappreciated IPEMU, the electric battery train that someone referred to earlier, has been criticised many times because nobody has bought it. Well, no one has bought it because there was never any need to buy it, because we never had any reason to change from using diesel trains. Now we do. We see the battery EMU finally becoming something contemplated in commercial operation, if not yet actually implemented. And that's where hydrogen comes as well. We seriously believe that there is a big place for hydrogen trains on the UK network. Notwithstanding what TDNS says, the ambition of the TDNS is admirable, but will be difficult to deliver and will take a long time. So that there's a transition period and there's the end state period, and both of those need to feature. Trains which we only know can be powered by hydrogen at the moment. Maybe in 25 years' time, a new technology will emerge. But right here, right now, it's the game in town, and so we feel it's imperative to get some fleets deployed and get them into actual passenger service, not demonstrations, not one-off trials, but let's prove that the technology can be made to work and start doing what happened with diesel. The first diesel trains did not roll out on a railway with a completely constructed diesel fueling distribution system. You have to roll out the infrastructure and the fueling support with the fleets, and we're prepared to do that. And that's really what our Breeze program is about, where we're working with Eversholt Rail to convert Class 321s. We've heard of all the merits of conversion so far, and that's equally applicable to hydrogen trains. and it gets us an available product sooner than other avenues might do. And so working with Eversholtz, we've now collectively invested a significant amount of money in developing a product, and importantly, crucially, as was highlighted earlier, developing a business case for the introduction of that product with a number of partners. A hydrogen train itself is ideally suited to replacing diesel. The one constraint we have currently remains the range, which is limited by that space requirement for the fuel. And as Brian pointed out, the range that we're able to achieve with these trains is significantly less than it is for a diesel train. A DMU achieves its long range simply by having more and more tanks, and you can extend the range by fitting more tanks. Of course, if you don't use them all the time, it's pretty inefficient because you're carrying a lot of unused fuel all the time and dead weight, but it gives you flexibility. At the moment, for hydrogen trains, that flexibility is limited to a 600-mile range. But that's pretty good for a duty cycle of a DMU on a daily basis. And as long as you can configure your operations on a return to base operation, or you have ultimately available fueling points, then that is sustainable. Speeds are up to 100 miles an hour. That's relevant to a DMU operation as well. And hybrid technology, again, we've heard all about it. It's a no-brainer with a hydrogen fuel cell, and that is what our technology is built around. Regen energy to give us the performance to arguably, well, we can beat the diesel performance in terms of acceleration with battery and fuel cell, and we can match similarly the refilling times and the process necessary. They're all weather systems. You can introduce a hydrogen fleet without disrupting service. And if you so wanted to, you could have a UK hydrogen train by 2024, a fleet in service. And that's what it would look like. This is the breeze. It's the identity that we've put onto this train. Of course, it will be in whatever operator livery chooses to operate it. And we will build them and convert them in the UK at Widnes. And doing that work in Widnes, committing to this technology now, means that the UK has a chance to actually get ahead. Yes, we could put off everything. Yes, we could wait till 2030 and deploy unproven technologies and take a risk. Or we could seek to embed the technologies now, understand how they work, optimize their operation, and then build a supply chain to support that. And that supply chain needs demand. Unless we start building the trains, there is no demand. There's no point innovating in the hydrogen space if no one's buying hydrogen kit. So there is a spreading benefit from deploying these technologies now. We have a chance for the UK to get ahead and build an export market, which we're so going to need. If we look forward and commit to certain things now, nothing's permanent, nothing's forever. Diesel wasn't, steam wasn't, I'm sure hydrogen won't be. Many technologies will come and go, but we have to commit and we have to make sure that we are able to keep the railway moving and make the case for modal shift going forward. And it's these kind of steps that will get us there. And that really is what I wanted to say. I fear I've run over, so I'll shut up now.
Not at all, Mike. I think you started a minute late, so thank you very much for an interesting presentation. I mean, I think it's quite telling, isn't it, how quickly the industry moved from coal and steam to diesel. It wasn't over a very long period of time. So, I guess we could see another rapid technology transition as we did, back in the 60s. But it's there for the taking, really. We just need to have the scale and ambition to make it happen. And I think that's one of the things that perhaps we can talk about in the Q&A later on. I'm going to move on now to our elevator pitches. And we're going to start those. So these are the sort of shorter 5-minute presentations. I'm going to start those with Matt Candy from Steamology, and he's going to give us 5 minutes on their technology. So Matt, over to you.
Hello, thank you. My name is Matt Candy, and I'd like to introduce you to Steamology. 10 years ago, the Steamology team broke the world land speed record for a steam-powered car. At the time, this was the oldest standing land speed record, and back in 1906, 127 miles an hour was the fastest car in the world, and it was a steam car. The project gave us experience in high-pressure steam and steam turbines, and we broke the record, but we didn't smash the record. And the car was fueled by LPG with flash boilers, and although advanced technology, not very efficient. So 5 years ago, we started to take a new approach to zero emission power. The combustion of hydrogen and oxygen creates clean, green steam. There is no NOx, no SOx, and no CO2 or particulate produced. The only product of combustion is hot steam. And this picture shows an open burner test. We are transforming water into power. Following the untimely death of the project sponsor for a new land speed record, Steamology has been exploring commercial opportunities for our water-to-water cycle. So we all know that renewable energy is plentiful, but it is intermittent. 10,000 times more solar energy strikes the earth every day than we use. And renewable energy can be used to power electrolysis, and electrolysis creates both hydrogen and oxygen gas. The gas is collected, compressed, and stored in tanks, and these tanks are our energy store, the battery of our system. So when the sun's gone down or the wind stopped blowing, the energy is demanded, gas is combusted, and it can go into our steam generator. The steam drives a turbine, and this can power electrical and mechanical power. Water is the only byproduct, and this can be returned to electrolysis. So we've got an effective energy system. And compared to hydrogen fuel cells, we have three distinct advantages at high power: significantly more energy dense, significantly longer life, and significantly more cost effective. Steamology technology is quiet and does not use any rare or toxic materials or specialized manufacturing processes. It's fully recyclable at the end of life. And we have 3 live rail projects. These are zero emission for both passenger and freight. And it's really picking up on that being less bad is not being good. These are genuinely zero emission. So we've developed a 100 kilowatt range extender. This is a modular unit that can power both batteries or direct DC traction. And we've worked on a project with Viva Rail. We've got a 600 kilowatt turbine in development at the moment. And this is going to be a steam electric drive solution using the existing traction motors at the megawatt scale for rail freight. So zero emission hydrogen freight. We're challenging the assertion that this cannot be done. We're also involved in a mechanical direct drive diesel engine replacement project in the 300 kilowatt scale, looking at a class 158 to retraction that engine with some amount of auxiliary and potential regen motor generator combined with an existing ZF gearbox. So we're working with Orosco, we're working with ZF, and this has the potential to relieve the potential stranded assets of so many DMUs that as we approach 2035 in Scotland and 2040 on the rest of the network. So we're retractioning today with the idea of new traction for tomorrow. So thank you very much for listening. My name is Matt Candy. Please let me know if you've got any questions, and you're welcome to come and see a demonstration of clean green steam down in Salisbury. And together we can make green power make a difference.
Thank you very much, Matt. I'm conscious of time, so I'm going to move on to our next presenter, which is Chris Smith, who's the Managing Director of Gvolution. Yeah, Chris, if you can unmute yourself and show your camera, that would be fantastic.
Working now. Hello, everybody. Thank you very much for listening. Trevor, thanks for inviting me. Gvolution has a concept really about evolving towards a zero carbon economy, which is a lot of people have alluded to the issues that face the railways in the UK and around the world. And this is our way of trying to evolve what exists to what hopefully will be. As moving swiftly to the second slide. Shall I try again, Trevor? There we go.
Yeah, don't double click it.
Thank you very much. This is, I think the challenge is fairly obvious to everybody. We have a lot of diesel-only trains. They're already sunk carbon. They've been built. Electrification or even hydrogen trains are very desirable, but they cost a lot and takes time. They don't always provide good value for money or energy efficiency for money, as well as the fact that air quality is a serious concern at many stations, especially in cities, as we've heard. So our idea is to take the existing technology, the diesel engines that exist in those contexts, the DMUs and the freight locomotives, and to combine with our technology cleaner fuels in co-combustion. So the optimizer, G-Evolution optimizer, will run an engine on diesel and another fuel. Could be natural gas and hydrogen, could be LPG or bio-LPG. It'll be a low carbon fuel. That means you get lower energy costs, you've got a business case to make the investment, you significantly reduce CO2 emissions, you improve air quality, but above all, you create a platform to allow the use of cleaner and greener fuels throughout the network. Under the feasibility we've done, we've shown that you can make significant net fuel cost savings, depending, of course, on the price of diesel and the price of the cleaner fuel. You can make significant carbon reductions, you can improve air quality, you can develop the infrastructure, and overall, you're producing a lot less carbon than you would by building something new if the vehicles that you're talking about have a life, which they often do, of 10 or 15 or 20 years. It's important to understand that, as somebody mentioned earlier, there isn't always infrastructure for cleaner fuels in place. This allows that infrastructure to grow, and the locomotive or DMU can run on diesel if otherwise required. We're working on two specific projects to demonstrate this. One is with the Grand Central Class 180 DMU, where we've built and very close to getting approved a dual fuel vehicle, which will run on a Grand Central logo from north of England to London, various stations. That should demonstrate fuel cost savings of 20% and payback of 3 to 5 years on the technology. That's what our demonstration shows. And we've also developed with Colas Rail and Network Rail, the first of a kind, a bio-LPG diesel dual fuel maintenance vehicle. That again should start, actually I say quarter 4, but maybe it's the beginning of Q1 2021, because everything takes a little bit longer than sometimes you might think. Again, that demonstrates that within 10 to 12 months, such a vehicle can be up and ready to run, and it's running on bio-LPG, which is not a fuel which is very much looked at. I haven't seen any charts in the rail industry, but it's a very low carbon, cost effective, and easily deployed fuel. In summary then, G-Evolution is really leading, certainly in the UK and in other countries around the world, dual fuel technology. We are working on projects both in freight and passenger rail, as I mentioned. Important point about natural gas and diesel is methane slip. We've got a tier 1 supplier working with us for a solution for that. But the benefits really are lower fuel costs, lower carbon, cleaner air, a payback, and a green fuel infrastructure to evolve so that in future hydrogen, bio-LPG and other trains can run cleanly and simply and easily. So thank you very much for listening, and there's more on our website, including a very good video if you're interested. But thank you, Trevor, for listening.
Thank you very much, Chris. I'm going to press on. I want to leave plenty of time for Q&A. So next we have Stuart Hillmanson from the University of Birmingham. Stuart, you are going to talk to us about Hydroflex. I hope that doesn't look like the right presentation to me. There it is. That's the one. That's the one I was hoping for.
Cool. Right. Thank you very much, Trevor. And good afternoon, everybody. I'll spend the next 5 minutes telling you a story of Hydroflex, the UK's first hydrogen train. And you can see it there going over a bridge over the River Avon. We were travelling about 40 miles an hour as we were slowing down, going into Evesham Station just at the end of September. Wait the 3 seconds. Here we go. Right, so why fuel cells? We've heard a lot about this, so I don't need to dwell on it too much. I think there's a growing consensus why fuel cells and hydrogen in particular is particularly good for fuel for the railway, and a recognition equally that it's never going to be as good as diesel. So we still have a problem. Future fleets for the UK, a lot of the current network is electrified, and we've heard already about the increase in electrification plans, but there's a big part of the country that has quite long distances between electrified sections, and hydrogen technology is the only viable option for a good part of these journeys. So that's one of the motivations behind this. We've also seen this slide already. This slide actually came out of our research group as we fed into the Decarbonisation task force from some RSSB funded work, and we can see there that you can make inroads through diesel hybrids and advanced hybrids, but the advantage about hydrogen is you can produce it with zero input from any fossil fuels at all. So the ultimate way of producing hydrogen is by getting some renewable generation, such as a wind turbine or solar installation, and connecting it to an electrolyzer, which produces your hydrogen. So that has zero carbon involved in it, and you just need to figure out how many wind turbines you need to run your train fleet. A fuel cell is different from a combustion process. It's naturally got a high efficiency. You put hydrogen into one side of the membrane, and the other side of the membrane is oxygen, and magic happens inside the fuel cell, and electrons are pushed around an external circuit which can do work and drive electric motors and so on. So we treat it as a black box where you put air and hydrogen in and get DC electricity out, which then you can integrate into any propulsion system that you want. What do they look like? So this is a picture of a Toyota car with a fuel cell in it, and the picture below shows the Ballard fuel cell that we've got in the Hydroflex train. So it is a box, and on one side of it you have a port where you can put hydrogen into it, and on the other side of it you have a couple of cables coming out, which is your DC electricity. You also have to manage the air that goes in, so the fuel cell has a compressor to compress air to react with the hydrogen, and you also have a cooling system, much like you would have on a combustion engine, to take away the waste heat, because the fuel cell isn't 100% efficient, and you need to get rid of quite a lot of heat, which of course could be used for passenger heating and saloon heating if you chose to. So what is Hydroflex? Well, we have been thinking about hydrogen trains at the University of Birmingham for a long time, and we realised, well, we started this work actually around about 2007, doing feasibility studies on this, and here are some pictures of narrow gauge locomotive that was developed to enter the Institution of Mechanical Engineers Railway Challenge, and we did that in our first year of entry. And on the left hand side you see our very first vehicle, and one of the key features of this is that we covered it in clear perspex, because as a university, one of our missions is to sort of demystify this technology, and right the way through it we've been very open and wanting to show people how the technology works, so they can see the fuel cell and the hydrogen and all the ports and input and output from a systems engineering point of view, to get people to understand the technology. Then 2 years ago at Enertrans, we launched a partnership with Porterbrook to take that technology and deploy it on Class 319, and you see us at Enertrans a couple of years ago where we agreed to do that, and we delivered the project in just 9 months. It's very much a team effort, and there you can see a picture of it after it was tested at Rail Live 2019, and there's some of the companies that were involved in the project. As I've said already, us coming from a university, part of us, our mission, if you like, is to disseminate technology and explain it to the public. So that's one of the reasons that we put the equipment inside the MSO vehicle, the motor vehicle. We took the seats out and put the fuel cell inside this vehicle with the storage tanks and the battery system, and allowed people to come and view it and poke around and see how it all really works. That's me done just about. There's just a couple more pictures of the fuel tanks. So that's real fuel tanks on a real train in the UK. and another picture of the fuel cell box. And we also have a battery system on board as well, 24 modules stacked in two parallel strings of 12 batteries each. And thank you very much.
Thank you very much, Stuart. I appreciate I had to race through the end there. Time was very, very short, so thank you for that. Without further ado, I want to move on to our last presenter, which is Paul Allen. I'm just going to give Hannah a moment to kind of, oh, she's done it, marvellous. Paul, please lead away, talk to us about what's going on at the University of Huddersfield.
Yes, thank you, Trevor. I just want to spend a few minutes updating on some new laboratory facilities that have been funded through a partnership with the University of Birmingham, actually. UCRIN, hopefully everybody knows a little bit about UCRIN. But as part of that, the University of Huddersfield leads the Centre of Excellence in Rolling Stock. And we're lucky enough to have about £8 million of capital investment through the government and UCRIN's partner companies to develop our lab facilities. So for those of you that aren't so familiar with the Institute of Railway Research, we're 35 research staff. We're established about 10 years ago now, so we've been going for about 20 years through Manchester Metropolitan University previously. I'm just going to make my slide work. A small overview of the Institute here. I'm not going to go into detail, but I just wanted to give you a little bit of background. So we're quite well known for vehicle dynamics, and you'll see something related to that when I show you our Harold test rig. Those of you who follow my Twitter feed will see updates on friendly Harold every now and then. So vehicle track dynamics is one of our specialist areas, but I'm focusing today on traction, braking, and energy systems because we're working on Harold 2.0, which is a development of Harold. Again, I'll explain that shortly. We also do quite a lot now with pantograph OLE dynamics, and we have a super duper new test rig, a £2.5 million test rig looking at pan OLE dynamics, a very important area in terms of minimising costs of OLE infrastructure, maintaining pantographs, etc. So I won't go into the full detail of the IRR. Please do contact me if you want to know more. I wanted to focus, as I say, on Harold. So Harold, it does stand for Huddersfield Rolling Contact Laboratory Dynamics Rig or something like that. So it is a meaningful acronym. But Harold was developed around our core area of wheel rail contact mechanics, adhesion, and braking. And if you can see, it's a little bit difficult to see, but there is a 2 meter diameter, it's a full scale rig, a 2 meter diameter roller here, and on which we can then run a bogie up to 200 kilometers per hour around this cylindrical disc. And we can give the bogie some attitude relative to the track to represent going around curves, and we can look at braking. But Harold was limited to some extent in that we couldn't really look at in detail at traction or energy recovery or hybrid systems, nor could we look at WSP. So we've looked to use some of the UCRIN funding to develop Harold 2.0. And I've just got a slide here, a little slide just identifying what that means. Well, what it means is rather than just having a trailer bogie, we don't really have any active braking system other than our own retrofitted freight braking system and rudimentary WSP that we developed ourselves. We're actually going to install a remoted Class 317 power bogie, which is going to be kindly donated by Angel Trains. This will be remoted and configured with an industrial drive converter. So what that enables us to do is rerun the vehicle with its full traction behavior, but also its electric and friction brake will be enabled, so we can run that in real time. In parallel with that, we'll be having a hardware in the loop system, which means that we can run hardware and software together in real time. And that enables us to really combine simulation and testing tools all in one test rig. And that software will include a train performance simulator. We can do whole route assessments for new hybrid drivetrains. We can look at duty cycles. We're going to develop some battery in the loop and fuel cell in the loop software models to really be able to look at these systems as a whole system. So before you go track testing new hybrid drivetrains, you can actually establish their performance and the capabilities of the system within a laboratory environment. But not only that, the new facilities allow us to look at in more detail at our braking research. So we've been doing quite a lot with RSSB, looking at better blending of the regenerative dynamic brake using the motor, the traction motor, and the friction brake blending. So that's quite important for vehicle manufacturers to be able to get that right. Looking at all electric braking and electric WS wheel slide protection, I should say, WSP wheel slide protection. We're also looking at developing advanced WSP algorithms and looking further into hybrid drivetrain development. So supporting some of the projects that you've seen here today. And always, we start off with some ideas, but we want lots more ideas. So please do talk to us and help us add further uses for Harold 2.0. Thank you.
Paul, thank you very much. Well, stay around. If I can ask all of the presenters to re-enable their cameras and microphones so we can see them, we'll go into our Q&A session. That's brilliant. Thank you. So I'm gonna ask a couple of questions that we have here in the Q&A chat. I'll also if you want to ask a question verbally, please raise your hand. There's a button to do that. So you can virtually stick your hand up and Milda will come to you and hopefully unmute your mic if you want to ask it sort of from the floor, so to speak. So whilst you're thinking and formulating your questions, I have a question here from Louise Shaw. She says, it's refreshing to hear the level of understanding among the speakers of embodied carbon.
Sorry, this is Milda. I have unmuted Louise so she can ask the question.
Oh, even better. Louise, do you want to ask your own question? Fantastic. You do more justice than I can.
Sure. Can you hear me okay, Trevor?
Perfectly, yes.
Good. Okay. So I've been very pleased and think it's very refreshing to hear the extent to which pretty much all of the speakers have said we need to be aware of embedded carbon in one way, shape or form. I think it's the first webinar or event I've been to that actually this level of acknowledgement has taken place. So that's great and well done, everybody. Thank you. But I think we still have a problem in that some fairly influential politicians, the likes of Hugh Merriman, for example, who's the chairman of the Select Committee, the Transport Select Committee, I should say, who doesn't seem to be getting this message or even the concept that this message is important. So what have we got to do to get across the message that betting on tomorrow's technology being perfection might not be the right idea, that we have a number of assets that could actually have a useful life and therefore not be economically disastrous. How do we get that message into the likes of Grant Shapps, Hugh Merriman and the civil servants?
Can I throw that to Mike Muldoon first up from Alstom? Mike, are you able to offer some thoughts on that?
Yeah, sure. I mean, I suppose we all have a collective responsibility to do it, don't we? You've heard all of us arguably pitching different forms of response to the same problem. We've all picked up though on some similar issues, and I think if that's the consistency of messaging that is translated across to the political sphere, then I think we have the opportunity to actually, be heard. The problem we have is that there are huge influences on politicians and huge influences on their policy making, and so all we can do is attempt to make sure that the correct messaging is heard. I know that sounds a bit lame, but I spend a lot of my time speaking to people like you and others, trying to pass over those messages, trying to make sure that is what those items are considered in the round. But I think for politicians, it's nice to have a simple answer.
Mike Edwards, I could see you were nodding away there as well as the question was being asked. Do you have a view from your perspective?
I don't think it's actually a unique problem. We've come from the automotive sector, and if you talk to anyone from BEIS or Department for Transport or wherever, they're all running around shouting hydrogen is the answer and sort of praying at the feet of something that might never quite get there. To the extent that lots of automotive grant funding specifically excludes new fuels, any work on new internal combustion engines, and quite frankly, that's just nuts. So I think to a degree, we have to get out there and demonstrate it to them. And hopefully they'll actually be listening to the industry. I think this is one of the first webinars I've seen where the industry are telling them how it needs to be, rather than it's normally with innovation, you get a bunch of big seats in government telling you how it's going to be. So let's hope they're actually listening.
Thank you, Mike. I guess anybody else on the panel, I want to throw over. Oh, one more. Whoever speaks first gets the option. Go on then, Jonathan. I think you.
I guess the one thing I would sort of say, and I think Mike, you hit it on perfectly there, is that governments will almost always go for solutions-based policy making, which is absolutely the wrong way to do it, because solutions-based policy making gives them the opportunity to seem like the hero who has the silver bullet that's going to fix everything. It's much better to stand up and say, I'm going to convert everything to hydrogen, and that's the great new future, than it is to say, I've set some targets and we're going to let industry work out what is the most pragmatic way to achieve those targets. But that is what we need to try and enforce as best we can. And certainly the likes of Ricardo do a lot of work with policymakers, EU policymakers, UK policymakers, and around the globe, in trying to direct policy so that it is based on targets, you know, with knowledge of what the technology can provide in regards to those targets, but it's still very much target-based rather than technology-based policy. And until we shift into that pattern, then it's going to be very challenging. But all I can say is we all have to keep banging that drum as best we can.
Okay, thank you very much, Jonathan. I've got a question here from Samuel Seabrook. Samuel, I think Milda's going to unmute you. If you can just tell us who you are and where you're from, and give your question to the panel, that'd be fantastic. Thank you.
Yes, hello everyone. My name is Samuel Seabrook. I'm an OCS graduate engineer at Mott MacDonald. My question is a bit of an open one to all those presenting about hydrogen. Whilst it does seem like a good technology until full electrification and battery can catch up. What the thing I've kind of seemed to see that's failed to be mentioned is the infrastructure that's needed at the depots. Say battery can just recharge off the overhead lines direct from the grids, but is that a shortfall where the kind of recharging at the depot might be a downside to hydrogen compared to batteries or full electrification? It's kind of an open question to anyone who'd like to answer.
I guess, Mike, you're probably a good place to answer as well as you, Stuart. So perhaps the two of you can field that one.
Yeah, I mean, it's interesting you say that to charge a battery off the overhead will be easy. Of course, we're talking about depots where there isn't overhead. This is replacing diesels. So unless you've electrified the line, and if you've electrified the line, you wouldn't want to charge a battery. So you've got to be very careful about these things. I think, yes, we have to introduce a degree of infrastructure with every hydrogen fleet that goes into place at the moment, unless or until a network of fueling stations is created through delivering fleets step by step. But the same goes, you can't roll out EMUs across the country because we've got to incrementally roll out the electrification. And the same for batteries. We can't, if we don't have charging infrastructure, we can only use them as very limited range extenders off the end of the wires so they can get back to the wires before the battery goes flat. So I think all of the technologies have infrastructure limitations. It's very easy to select hydrogen for that critique, but actually they all apply. But I totally agree. There is not a silver bullet, as I think the previous question as well. All these technologies are complementary, and please don't think that Alstom has a particular favourite amongst these. We actually offer all of them, but we have to offer them as appropriate to the customer needs in the right locations.
Stuart Hillmanson from University of Birmingham. Do you have any views on that?
We have the Hydroflex train, and that's obviously operational and running, and we have developed our own refueling system. I think that the excitement behind the refueling isn't as exciting as seeing a train going across a bridge, but it's equally as challenging to develop the infrastructure required to fuel a hydrogen train. So we've developed that in partnership with a company called Fuel Cell Systems, and we're now working with a company called TP Group to advance that to develop refueling systems for full scale hydrogen deployment, and that's progressing really well. So it's something we have been thinking about, and it is a very important piece of work that needs to be done to kind of harmonise that across the industry. And to that end, we did do a piece of work called Hyd Energy, which was an RSSB funded project. You'll be able to find it on the RSSB website, the Spark website, which looked at depot and infrastructure requirements for hydrogen deployment across the country. So the industry is looking at this, and I think there's no kind of showstoppers that will stop us doing this, and there's lots of people that can supply hydrogen at railway scale grade, railway scales and the required grade to make it viable.
Okay, thank you. Matt, I'm going to come to you very briefly. I'll give you 20 seconds if you can just add on to that.
Okay. Yeah, I think it's about adopting distributed power, which local electrolysis from renewables can do, and it's taking a long-term view. There's not enough batteries have an energy density problem, and they have a toxicity and a scarce materials problem. So we're coming at it from a clean energy point of view, long-term recyclability.
Okay, our next question is, oh, sorry, go on, very briefly.
We've done a lot of work on hydrogen as a fuel additive rather than hydrogen as the end result. So again, it's that sort of roadmap. Is hydrogen the end game? Is there a way of using hydrogen earlier in the innovation cycle? We took a class 20 locomotive, put various bolt-on technologies on it, including hydrogen electrolysis, and reduce the emissions by well over 60% and increase the power and change the fuel efficiency quite dramatically. So hydrogen infrastructure, it's coming. Hydrogen as a fuel and a fuel additive is already here.
Yeah, thank you, Mike. So I've got a question from Jennifer. Jennifer, please, hopefully you're unmuted. Please ask your question and tell us where you're coming from as well, please.
So I'm Jenny Cook. I'm currently studying at the University of Birmingham, and I am wondering if the panelists can give me their opinions on how the UK is doing at its decarbonisation strategy for rail compared with other European countries. And yes, that is the title of my dissertation.
I'll throw that open to the panel. Anybody want to answer that one?
I think I might already have answered it in the written questions, but
you've given me great stuff to go on, Mike. So if other panelists want to jump in, that would be great.
I think one of the challenges that we're facing is that we have a different set of problems here compared with Europe, partly due to the gauge of our locomotives. So hydrogen trains in Germany, for example, sometimes they put hydrogen underneath, but there's also a lot where they put it on top, and we physically can't do that. So we have a completely different set of logistical issues. From what I can see in the hybridisation, we're actually ahead. There are lots of companies, particularly in Germany, that are working on it, but I think we have a lot more different technologies for solving the same problem than most places.
Thank you, Mike. Unfortunately, our last question asker is actually gone offline now, but I will ask his question. It's Philip Dixon, and he asks, is there any thoughts on fast charge batteries with fast charge pads at each of the stations along the line? So I guess it's a kind of charge whilst in transit type approach, where the trains can partially charge during loading passengers. I mean, I guess you could do it with OLE, it doesn't have to be pads necessarily, but you get the concept. Has anybody thought about that from, I guess, an OEM rolling stock perspective or a Roscoe perspective might be useful to have on that? Brian,
from an OEM perspective,
I was going to say I could jump in there, but Mike put his hand up first. But certainly I've been watching the Viva Rail technology with interest. Certainly third rail fast charging. It's something I've put an answer in the chat actually about the fact that our hybrid has been designed as a plug-in hybrid, and that plug doesn't have to be a physical plug. Obviously, it can be a pantograph or it can be a third rail shoe. So it's certainly something we're considering. We're walking before we can run, first of all. So the Chiltern trial won't have that available, but it's certainly something we're thinking of for terminus stations and for depots. And I think Mike actually mentioned it a moment ago, saying if you want something that isn't there, you're not going to electrify the depots. Well, yes, you could actually. Why not electrify the sidings and the stabling yards? Because you don't have to have the engine running. You can charge the batteries fully and then go out with a fully topped up charge.
Yep, and I think that sorry, go on.
I was just going to say the only reason, all I was saying was you have to electrify the depot. I think the technology for fast charge and at each stop already exists. We already offer it, but we offer it on light rail, on trams in particular. because the amount of charge you can charge in a suitable dwell time is viable, and the amount of energy you require to move to the next stop is equally viable for that type of operation. The bigger the train, the greater the amount of charge you've got to transfer, the greater the loads, the bigger the grid connections. You're actually involving a lot of difficulty. You might say it's easier to electrify in the final analysis in a more conventional sense. So you've just got to, as always, you've got to evaluate case by case and see what's possible.
And I'll add to that, actually, sorry, just on the dwell time side, the thing that we're driven for most of all is to get that dwell time down, and therefore we're eroding any inter-vehicle charging anyway.
Yeah. There's actually so Jonathan, I was about to name check T1160. If you're about to name check it, then please go ahead.
No, I was actually about to do, well, T1160, yes, but actually there's a previous piece of work we did for the RSSB. It wasn't publicly issued, but they asked us to have a look at inductive power transfer methods. So that is back to the original question about wireless charging. So it's something we've looked extensively at and done a huge piece of work for Highways England on in the past, and delved into it a little bit in rail. Inductive charging really can't at this stage provide the power where you can get up to possibly about 1 megawatt of charge, which for a high power battery, for a traction battery on a battery electric only train, wouldn't be sufficient to charge a battery quickly. You need a lot more energy than that, 2, 3, often more megawatts. Equally, the other issue is if you are doing these very high power charges, imagine you are at a station in a small town and a train comes in and suddenly demands 3 megawatts to charge the battery for 30 seconds. The grid infrastructure is not going to appreciate that very much. So the other issue is how you balance the power demands of those sorts of very sporadic, very high power intensity charging operations, which normally means
Jonathan,
you have to stop another set of batteries on the line side. Yep,
I'm going to have to stop you there. I'm going to stop you there. We have reached our time. I just would like to extend my personal thanks to all of the speakers and panelists. I've been very interesting presentations. All of that material, the recording from the session, should be available tomorrow. Yeah, we are back tomorrow looking at decarbonising operations, maintenance and renewals. And Richard Jones will be leading us through that tomorrow afternoon. So thank you very much, and we'll draw things to a close there.
Thank you, Trevor.
Thank you.
Thank you, Trevor.